All right, so hello everyone. Welcome back to your ContextFree 35 tutorial. So maybe some quick announcements before we get started. So in case you didn't notice, I posted an extra video and actually an extra tutorial recording, which is a recording that I had done for the last summer semester I taught 335, and it's basically about a couple of things. So the CFG to PDA kind of conversion algorithm. It also covers DPDAs and closure properties of context-free languages. So obviously you've probably noticed that there's a lot of material and there's a limited amount of time in the tutorials. So because we didn't think we could cover these effectively during, we decided to post some extra videos. So these should be helpful to you in solving the assignment. So that's why we also posted them. The next, right. So then the next announcement is that because your assignment includes Turing machines, and this tutorial we're not going to actually cover Turing machines. We're just going to do the pumping lemma for CFL. We're also probably going to post a Turing machine video, so that since the due date is Wednesday, you can actually have some time, I guess, tomorrow to look at it, in case you need help for that part of the assignment. And then the last thing is that the marking for assignment 3 might be sort of slightly delayed, just because the other TA had some personal difficulties that she kind of had to sort through. So that's why we might take a bit longer to mark this assignment. That's just an FYI, okay? And no, this is not the last session. The last session is Wednesday. So that's the last tutorial. Okay, so that's it for announcements. So actually, let's get into some course material. So the pumping lemma for context-free languages. So essentially, to give you some context, we've essentially seen that we have a set of languages like L, A star, B star, like W, such that AB is a substring of W. So we have an infinite number of languages which are regular, okay? And then we've seen that there exist languages like AN, BN that are not regular, but that are context-free. So we have context-free languages. And then what you saw during the last lecture is that there are also languages that aren't regular and that aren't context-free. So in other words, languages that are here, so not context-free. Like, for instance, like you saw in class, AN, BN, CN for n greater or equal to 0. Okay, so there's some languages here that exist, and to prove that they are not, so to prove that they are not context-free, you need a similar method as what we did to prove that something is not regular. You need to use a pumping lemma. So this is just an equivalent version of the pumping lemma, but applied to context-free languages. Okay. So what does that actually look like? So the pumping lemma for context-free languages is slightly more complicated. So it's your standard initial definition, or initial lemma. So suppose L is an infinite context-free language, then there will exist a constant m, which is strictly greater than 0, such that for any w in L, with the length of w being at least m, we can decompose w as, in this case, uvxyz, right? So you remember that in the pumping lemma proof, we only had sort of 3 elements, so we had X, Y, Z. But now in the pumping lemma for context-free languages, we have a decomposition into 5 substrings. Okay, and so we have 2 conditions on these substrings. We have that Vxy is at most m, so the length of Vxy is at most m, and the length of Vy is at least 1. Okay, so we can decompose W into something like this, where this and this hold, such that if you pump W up or down, so in other words, pumping up or down in the pumping lemma for context-free languages looks like Vi, Yi. So for every I, we can show that Wi, or the lemma tells us that for every I, Wi will be in L. Okay, so that's what the lemma tells us, right? So, okay, that's very nice. So how do we actually use this to prove that a language is not context-free? So the first thing that I'm going to mention is similar to the pumping lemma for regular languages. The pumping lemma for context-free languages can only be used to show that L is not context-free. So you cannot use the pumping lemma for context-free languages to show that L is regular, context-free, sorry. And the reason why I'm going to mention this again is because people didn't fully understand this in assignment 3. In assignment 3, there were a lot of, or at least in the section that I corrected, there was a lot of people who used the pumping lemma to prove regularity. And so that is never correct. That's never going to be right, okay? But this occurred quite a bit in the proofs for the pumping lemma. And so just to warn you again, you can never use the pumping lemma for regular languages to show that the language is regular. And you can never use the pumping lemma for, let's say this is for context-free languages to show that something is context-free. So you can't do that either, okay? So how does the pumping lemma to disprove that something is context-free work? So again, like the one for regular languages, you assume for the purposes of contradiction that L is context-free. The next step is you need to pick a W in L such that the length of W is at least M, the constant in the pumping lemma for the context-free languages. And similarly to the regular language pumping lemma, picking a particular constant or picking a particular length for your string is never correct. And unfortunately, this was also not very well understood in assignment 3. I had a lot of people doing something like W is A, B or something like that. So this is never correct. Your string W must be, so it must be a function of M. So the length of W has to be a function of M, okay? So pick a W accordingly. Next, so you'll remember that for regular languages, we decompose W into X, Y, Z. In this case, we're going to decompose it into UV, X, Y, Z. But now because the decomposition of VXY, which is what we're going to pump up or down, is in the middle of the string, then we're actually going to have to consider more than one case, okay? And so for each case, so for each possible decomposition, you need to pick a particular pumping length or sort of pumping number, I, such that when you pump the string Wi, it won't be in L, okay? So it's very similar to the regular language one, except that now it's for each possible decomposition, okay? And so if you do it for every case, and that your cases together exhaust all possible cases, then you've shown that for every case, there is an I such that Wi is not in L, which leads us to a contradiction, which implies that L is not context-free. Okay, so that's how you use the pumping lemma to disprove something is context-free in theory. Now let's look at an example. So I have an example here where I want to prove that the language an bn factorial is not context-free. Okay, so here the choice of w is quite natural. It's just going to be am bm factorial. Okay, so we can pick that as our string. So then what does our string w look like? It looks like a bunch of times, so exactly m times, and then b m factorial times, right? Okay, so now the trick that I use for the decomposition for context-free languages with the pumping lemma is, so we know that w has to be decomposed as u, v, x, y, z. Basically, what you need to do is you need to use this string here, the string that's actually important, and you need to kind of scan it through your whole string and identify all the possible cases. Okay, so what are the possible cases? So there's two very obvious cases. There's one case where vxy is within all of the a's, so that would be case 1. And then there's another case where vxy is within all of the b's, right? So we have these two first cases here, right? So in the first case, so in this first case, what we have is we have that vy is equal to ak, so just ka's, right? For k greater or equal to 1. Right? Okay, so then if you wanna pick an I to get a contradiction, well, here it's actually not that difficult. You can, in this case, pump up. So pumping up is going to do what? Here I decided to pump up, so I get W2. W2 is U V2X Y2Z. So in other words, it's U, V, V, X, Y, Y, Z. So what that means is that just imagine that here I'm adding an extra V, and here I'm adding an extra Y. So that means that together, because the length of Vy together is K, then I'm going to be adding KAs to my initial MAs. Okay, so then W2, so W2 is then going to be A m plus k b b m factorial, right? Because I don't touch the number of b's, right? So then all that's left to show is to show that this is not an L. So why is this true? This is true because m plus k factorial is at least is greater than or equal to m plus 1 factorial, right? Because k is at least 1, which is strictly greater than m factorial. And so clearly, if you have a number is strictly greater than another number, then of course it can't be equal, right? So that means that m plus k factorial is not equal to m factorial, which leads to a contradiction. Well, it leads to the fact that W2 is not in L, which leads us to a contradiction, okay? So this is a contradiction just for this case. So the idea is that you need to repeat the process for all possible cases. So that's why the pumping lemma for context-free languages is a bit more annoying, right? Kind of quite naturally. Okay, so that's for this case, right? So we have the case where you have v, x, y is within the a's. You have a similar case where you have v, x, y is within the b's, right? So in that case, you have that vy is just k b's, let's say, for k greater or equal to 1. Then in that case, you can also, let's say, just pump up. Pumping down could also work. So if you pump up, let's say you get W2. Then W2 is you're adding k b's to your already m factorial b's. So you have am b m factorial. And now you're adding, right? You're adding k b's because you're adding a vy, right? So that gives you this string. And clearly this string is not an L because if you take the number of a's and you do factorial the number of a's, so m factorial, then that's not equal to the number of b's, which is m factorial plus k, because k is at least 1. Okay? So that would cover case 2. So then you get a contradiction for case 1 and for case 2, and so now you can move on. All right? So, so the next case, right? So remember, we're still dealing with A's and then B's, right? So what's the next case if you're sort of sliding Vxy? Well, the next sort of natural case is Vx. So the X is between the A's and the B's, and the Y is in the B's and the V is in the A's, right? So that's your next case. So for that case, you have actually subcases to consider. So why do you have subcases to consider? Because you only know that together the length of v and the length of y. So together v and y have length greater or equal to 1. But now it's possible that the length of v is 0 or that the length of y is 0, right? But in either of those two cases, right? So if the length of y is 0, if the length of y is 0, then you're just going to pump your a's. So that's the same as case 1 here, where you just pump your a's. If the length of v is 0, then that's the same as case 2, where you're just pumping your b's, right? Because the only thing you could pump, right? Let's say you had W2. The only thing you could pump if v was empty would be y. So then you would just be pumping u, v, x. So this would be 2, this would be 2, this would be z. But this is lambda, right? Because the length of v is 0. So because it's lambda, you're actually not considering this, so you're just pumping up your v's. Okay? So now the actual interesting case that we care about is the one where both v and y aren't 0. So in other words, the length of v, let's call it k1, is strictly greater than 0, and the length of y, let's call it k2, is strictly greater than 0, right? So we know that their sum is at least 1 and at most m, right? So now if we pick, let's say we pump up. So if we pump up, so we have W2, so that's u, v2, x, y2, z. So that, what is happening here? Here you're going to add, so to this v, you're going to add another v. So in other words, this is equal to adding, you add k1a's, right? And then to this y here, you're going to add an extra y. So you're going to add a y, which just means you're going to add k2b's, right? And so what that means is that you're going to have m initial a's plus k1a's, and then m factorial initial b's plus k2b's, okay? And then all that's left to show is that m plus k1 factorial is different from m factorial plus k2. Well, in fact, m plus k1 factorial has to be strictly greater than m factorial plus k2 because m plus k1 factorial is at least m plus 1 factorial, which is equal to, say, m plus 1 times m factorial, which is equal to m times m factorial plus m factorial. And so that's clearly greater than m factorial plus k2. because K2 can be at most M. And so it's not difficult to notice that M times M factorial is greater than M. Assuming M is, let's say, greater than 1, which it has to be. Okay. So, so then that would show for this case, so for case 3, where X is A's and B's, where V is A's, Y is B's, that you also get a contradiction. So this leads you to a contradiction. Okay. Then there are 2 more cases, which are a bit easier. You have the case where now, instead of the X being the A's and B's, the V is the A's and then the B's, right? So then it's just easy to pump up and get a contradiction, because if you pump up, you're just going to get A, B. So this is your first V. And then again, the same thing. So this is V, A, B. And then you're going to have some more B's, right? So then this doesn't look like, right? This isn't A's followed by B's. This is A's followed by B's followed by A's followed by B's. So then this doesn't look like anything like this. So then it's easy to just claim, or to just say that it's not an L, because clearly you can see that it's not. Okay. And then it's the same idea for Y. So if Y instead is within the A's and the B's, then you can use the same argument that you get kind of a mismatch, right? So things don't look like A's and then B's, so you also get a contradiction. So then for every possible case, you get a contradiction, which implies that L is not context. L is not context-free. Okay, so the question about the final review class is, so that's probably going to be a yes. I just need to make sure of a date. And then do we need all cases to reach contradictions to say language? No. So you need to show a contradiction for every case, because it's possible that for one case, so it's possible for one particular case, like for instance, actually, let me give you an example. Let's say you're using the language ANBN, right? And you wanted to show that this was not context-free. So we know it is context-free, but let's say you want to use the pumping lemma to show that it's not context-free. So there's different decompositions, right? So one which would give you a contradiction would be if VXY was here, right? Another one where you would get a contradiction is if VXY was here, right? But one where it would be impossible to get a contradiction is if X is here, V is here, and Y is here. So why is it impossible to get a contradiction? Because you can't guarantee that the length of V is not equal to the length of Y. Okay, so because you can't guarantee this, then if you pump up or down and it actually happens that the length of V is equal to the length of Y, then you'll never get a contradiction. So you have to show a contradiction for all of your language, of all your cases, okay? Because if you don't, right, if you can't get one, then it doesn't mean that it's context-free, but it means that maybe the string you picked is not right, or you might be onto something and it is context-free. Okay, but you can never, again, I'd like to state this again, is you can never use the pumping lemma for CFL to show that something is context-free. Okay. But yes, so you need to show for every case.
Sir, I'm still a bit confused. Like, why? Okay, I get it. Why we need to show it here, but what's the difference with the regular pumping lemma?
Yeah.
That makes it so that we don't need to show every possible case for that.
Yeah. That's a good question. So for the regular pumping lemma, your decomposition is W is X, Y, Z, and XY is at most, the length of XY is at most M. So the reason why there's no cases is because what you're going to pump up, which is Y, is always in XY, right? And XY is always the first M, I guess, symbols in your string. Symbols in W. So like for instance, in this case here, if you have AM, BM, you're not gonna, right? You're not gonna move your XY at different places. Your XY is always at the beginning of your string. So it's always the first M, at most the first M symbols of your string. Whereas in this, right? So in this pumping lemma here, because I have U, V, X, Y, Z, U and Z, I have no information about U and Z. For all I know, you could be lambda, you could be 3 A's, you could be A's and then B's, and then the same thing for Z. Okay, so that means that you have to consider, oh, VXY is here, because maybe U is just a few A's, or maybe VXY is here, because maybe U is all of the A's.
Okay. I get it. Okay.
You get it? Good.
Yeah.
Good question. All right. So now let's see if things are clear. So I'm gonna let you do this exercise. It's not realistic for you to like write out all the proof, but what I'd like you to think about is picking a W. And so that's the first thing I'd like you to do. The second thing I'd like you to do is what are the possible cases? So you can kind of do it like I did, like you write out your string and you can say, oh, maybe VXY is here, or maybe VXY is here, and then how is this a case? And then for each case, do you pump up or down? Okay, so I'll give you 2 minutes because this is an involved exercise, and then we'll look at it together. All right, so let's look at this question together. So I wanted to pick a string W, where of course the length of my string needs to be greater or equal to m, and it needs to be a good candidate for getting contradictions. Okay, so does anyone have a choice to volunteer?
AM, BM, CM minus 1.
Yes, very good. That's exactly the one I was going to go for. So I guess I don't have to think of a reason or sort of think in place. So that's good. Thank you.
So is there a difference if you pick AM plus 1, BM plus 1, CM?
No. Okay, so that's what I was looking for. So yeah, that's also a very good choice. It would also work very well. Yeah, very good. And actually the order of your strings doesn't really matter, right? So it could have been AM, CM minus 1. Well, could it have been? Maybe not actually. Actually, we'll answer that question at the end because that's a good quiz question. So we'll answer this at the end. Could we have picked? So just so I remember, could we have picked this? But for now, let's actually just stick with this, okay? And let's go through the different cases. So there are some quite obvious cases. So if I have W, say, is a bunch of A's, so let's say it's exactly M A's, and then B, it's exactly M B's, and then C's. So it's exactly M minus 1 C's. There are some obvious cases like VXY is just A's, VXY is just B's, and then VXY is just C. Okay. So I'm not going to go through the whole proof sort of process because that would take a really long time, but we can just sort of talk about it, is that for either of these two, it doesn't really matter if you pump up or down, because if you pump up, then for either A or B, you're going to get that NA is not equal to NB. And if you pump down, so if you pump down, then you'll either get NA is less than or equal to, well, actually, you'll also get NA is different than NB. So you get this, and you'll also get NA is less than or equal to NC. But of course, just one is enough for the pumped string not to be in L, right? So in these three cases, so this is case 1, 2, and 3, you would arrive at a contradiction, pumping up or down for these two cases. And then for this case, actually, for this case, doesn't matter if I pump up or down. So if I pump down, right? So if I pump down, I'm just going to reduce the number of C's, right? And so that's not going to get me a contradiction. So down would not work, So here you have to do this. So you must, let's say, pump up, because you'll get that NC is greater equal to NA, which is equal to NB, right? Which will, so let's say if that was W2, then that will not be in L. All right. So of course, if this was so don't like this is good to sketch out the proof, but don't do this in your assignment. If in your assignment, actually write like basically what I write here. So make it rigorous, but to get you an idea, you can do this to sketch it out quickly, right? So that's for those three kind of obvious cases. Then there are a few more, let's say, quote unquote, obvious cases. So there's one like the one in the previous exercise where you had, let's say, X was within the A's and then the B's, right? So it's A, B. And then you had V is A's, and then y is b's, right? So there's this case, it said this is case 4. So let's assume, so we're going to assume that the length of v and the length of y are non-zero, right? Because otherwise, similar to the example, otherwise then it would just reduce to a case here. So we can assume that v, the length of v is not 0, and the length of y is not 0, right? So then in that case, you have the length of, so v is just k1a's, and y is, let's say, k2b's. Then you can't, so pumping up would be wrong. So pumping up would not be right, because you would get something like a m plus k1, b m plus k2, and then c m minus 1. But then you have no way of showing that m plus k1 is different than m plus k2, right? So there's no way to show that, okay? Because you can't control k1 and k2, right? And so you have to pump down. You have to pump down so that you get a m minus k1, b m minus k2, c m minus 1. So then your number of b's or your number of a's is less than or equal to your number of c's, which implies that this is not in L, right? So that gives you a contradiction. So that's case 4, okay? Then case 5, very similar, but now your x is just going to be in the B C's. So let's say V is a bunch of B's, and X is a bunch of B's, and then a bunch of C's, and then Y is a bunch of C's. Okay, so then what you have, V is BK1 and Y is CK2. So let's assume that K1, K2 are different than 0, because otherwise, if they weren't, so if either of them were 0 or both of them, well, both of them can't be 0, but if K1 was 0 or K2 was 0, then it would just simplify to a case that we've already seen. Okay? So then can we pump up or down? In this case, it doesn't really matter what you do, right? Because if you pump up or pump down, you'll get that NA is different from NB, which would mean that WI is not in L. So that's a contradiction. Okay. So again, I'm sketching this out. This isn't a formal proof. Don't do this in your assignment. But it's just to give you an idea. Okay. So that's cases 4 and 5. We have maybe. Oh, right. Okay. So then we have one maybe last case. So the last case is, let me actually scroll to it. So then the last case is your V's are now actually, so instead of your X being the A's and B's, it's now the V that's A and then B. Okay. And this would be the same if Y was like A and then B. So you would just use the same argument here. And so in this case, you can just pump down, and then you'll get that your number of A's and B's sort of together, or just either your A's or your B's will be, the number of those will be less than or equal to the number of C's, right? Because you're decreasing the number of B's and A's here. And because there's M, A's, and B's, if you decrease it at least by 1, which you're doing, you're going to have that the number of C's is greater or equal to the number of B's. All right. And again, the same thing would happen if Y is A's and B's, right? So that's why I'm not going to actually mention that case. So then the other case is then the B. The V is the B's and the C's. So again, very similar to previous cases. So you can kind of see how this becomes mechanical once you find all of the cases. In this case, pumping up or down will work because then the number of A's will be different from the number of B's. All right. And so since for each possible decomposition, we can find the particular I such that wi is not an L, i.e. for each possible decomposition, we have a contradiction, then L cannot be context-free. Okay? So any questions about this? No questions? So now let's go back to what I asked before is, would the order have mattered here? So if I had said W was AM, CM minus 1, BM, so would that still have worked? Does anyone want to answer, or does anyone have an idea?
Yeah, I mean, it would be the same concept, right? Like you would try, I think maybe your possibilities would be less, maybe, but
Yeah.
you would still pump down like your A's or B's so that it would be less than C's, and for the C's you would pump up so that they would be.
Yeah, I agree. Yeah, so in this case, this string would also work. Yes, very good. All right, so okay, so it doesn't seem like, other than the fact that this is a painful concept, and I agree it does make your assignments a lot longer. But other than that, I feel like if you if you're able to, of course, the trickiest part is finding the W, but once you have the W, then, you know, with the trick of sort of scanning, you just look at all the cases, you think pump up or down, and then you get a contradiction for each one. Okay? So, so that's that. Now, another question which actually might look familiar, where it's another proof that it's not context-free using the pumping lemma. So this one I'll give you a bit less time for a reason that you'll see in a second. So I'll give you a minute, try this one out, and we'll look at it together. All right, so why did I say that this example looked familiar? Well, there's two reasons. The first one is because if you look at this proof, then it's going to be very familiar to the one for showing that this language is not regular. So what do I mean by that? Here, a natural pick for W would be, say W is AM square, okay? So of course, writing, you know, the assume for the purpose of contradiction that this language is context-free, yada, yada, yada. Okay, and then we get to the interesting bit where we pick a W, right? So this is picking the W. W is, let's say, AM squared. Then we decompose, right? But in this case, it's very easy to sort of decompose because if you have W is U, V, X, Y, Z, but the string is only just A's, then of course V, X, Y is just a bunch of A's. And so more specifically, Vy is just AK for K greater or equal to 1 and K at most M. And so what's nice about this is that there's only one case. right? Like how it is in the one for regular languages. So then, because you only have one case, then the logic is exactly the same as how you would prove this for showing that this isn't regular, right? So the third step is pumping up or down. So you'll probably sort of notice here that it doesn't really matter if you pump up or down. So here, let me say that I'll just pump up. So if I pump up, then let's say I pick I equals to 2, so I have W2. W2 is U, V2, X, Y2, Z. So basically, this is add KAs to M square A's, right? So then W2 is just A M squared plus K, right? And so the idea is now you just need to show M squared plus K is not a perfect square. Oh, come on. Perfect square. There we go. Okay, so right, so how do we do this? I mean, this is almost copy paste from the lecture slides. How do you show that M squared plus K is not a perfect square? You just show that M squared plus K is strictly greater than M squared and strictly less than M plus 1 square, so that it's in between two consecutive squares, right? So I'm not going to put the details because the details, I mean, hopefully you already know them. But so this of course sort of leads us to W2 is not in L, which is a contradiction. Okay, so then what does this mean? This means that L is not context-free, right? Okay, nice. So what was the purpose of showing you this example? The purpose was that because the procedure basically is exactly the same, bearing maybe the fact that here you have a different W, but the procedure is exactly the same to show that sort of the language isn't regular, right? And so what this means, and what you can conclude from this, is that if you have a language L, which is over a singleton alphabet, so in other words, it's over a single string, and L, so if L is not regular, right, then it means you could sort of go through this kind of proof. And so you can, of course, go through the same proof to show that it's not context-free. So L is not regular implies that L is not context-free, right? So this is definitely not true in general, but if sigma is just a singleton, then this idea shows you why this is true. Okay. So something to keep in mind, right? So I said at the beginning, there's two reasons why this should look familiar. So that was the first reason. And the second one, I'll let you guess why I said that. All right. Okay. So, but any questions about this? No questions? Okay. So, well, in that case, we're at the last exercise of the tutorial. So we want to prove that the language L here, which is 3 consecutive same strings, is not context-free. So here I'll give you a hint. The idea. What's the hint? The idea is to use the closure properties. And specifically, you want to use the closure property that if you have a language that's context-free and you intersect it with a language that's regular, then it'll give you a language that's context-free. Okay, so you want to use this first before using the pumping lemma. So that's the hint, right? So I'll give you 2 minutes to try this out, and we'll look at it together. All right. No, not time to drop. I don't like the sound of that. Especially because in the exam, which is multiple choice, you're obviously not going to have to do this, right? I mean, you're not going to have to do the proof, right? So, oh wait, what? No, I actually, he might. I actually don't believe he would do that, but okay. I mean, all right. I mean, I'm surprised. Maybe it's like MCQ, like I don't know, like fill in the blanks, like like not fill in the blanks, like give a number or something like that. But because the whole reason why it's not MCQ, well, all right, okay. Well, okay. In this case, then let's try to understand this question like correctly. Okay. Because in that case, the assignments will also be helpful. How would they go? Okay. So then I like that this is the most participation during the whole tutorial, but let's try to look at the exercise then carefully. Okay. So what was the idea here? So you have sort of www, right? So the idea is kind of to to think of the fact that, so what's the idea behind AN, BN, CN is not context-free? The idea is that you can track the number of A's, and then you can track the number of B's, but then the number of C's, you can't track that because you'll have pushed your A's and then popped your B's, right? So that's the idea. So I'm just going to use the same idea here. The fact that I'm going to intersect it is just going to help me get kind of a concrete example, right? Because it's very difficult to look at something like this and come up with a string, right, W. But if you intersect it, then it's a bit easier, right? So here, what I'm going to intersect it with, but this isn't a unique choice, is let's say A star B, A star B, A star B, okay? So I'm going to intersect it with this. I'm using this B to separate the A's here, so that the resulting language is ANB, 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 for n greater or equal to 0. Okay. So why is, yeah, so why, so the idea behind this pick, right, is very similar to the reasoning behind AN, BN, CN, right? Is that here you can track the first A's, then you can track the second A's, but there's no way for you to track the third A's. So then here you get a much more natural choice of W. Here, the choice of W could be AMB, 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 right? And then from this pick, hopefully it's a bit easier to see how you could get subcases, right? So of course, this is a very long question to do, right? But the idea is just to try to help you to see how you can start with something sort of like this, use closure properties, then start with the pumping lemma, and then look at all the cases, right? So here, what are the cases? So I have A's, and then I have B, and then I have A's, and then B, and then I have A's, and then B. Right, I have MAs here, here, and here. Right, okay. So some easy cases, right? VXY is here, VXY is here, VXY is here, right? That's easy, right? Because in that case, you can either pump up or down. It doesn't matter. You'll just have that that specific portion of A's has a different number of A's than the other sort of two portions, right? So that's three cases, right? Three cases down. that would be case 1, 2, and 3. Okay. Then what are my other cases? So I don't know this. Let's say. Right. Okay. So the other set of cases is let's say your x's. Let's say your x is here, and your v is here, and your y is here. Right. Again, that's actually not that hard, right? You can either pump up or down. If you pump up, you'll get more a's here and here, assuming that these two aren't empty, because if either of them are empty, then it just goes back to case 1, 2, or 3, right? So then assuming x is just within this, then for Vy, if you pump up, then you'll just have that this number of a's is different. If you'll pump down, you'll just get the same result, but you'll just have less a's for V and Y, right? And so the same idea happens if your x is here, right? So that would be, let's say, cases 4 or 5. And then you have the sort of easier cases, I would say. The easier cases would be if your V looks like something like A, B, A, right? Or Y looks like A, B, A, right? So in either of these two cases, if you pump up, you'll just get a string that doesn't look like this, right? Because pumping up will allow you to add like an extra sort of A, B, A in your string, right? You would add an extra V to your existing V, right? So you would kind of get a string, a pattern mismatch rather than a length mismatch, okay? And so then if you say something like this, honestly, for your assignment, actually, if you said something like this, and you said, like there are several cases where your V's can be A's and then B and then A's. In all of those cases, you can pump up and get a contradiction. And then if you say the same thing for Y, then for me, that's enough, right? So for me, this in terms of cases is enough. So I think listing them like this is actually kind of a waste of time, to be honest. So you don't need to go that into depth, right? Because here, it's really the same thing. Here, V is A's and B's. And here, I'm just sort of repeating the same thing. So it's just kind of a waste of space. If you just get the gist, if I see that you've got the gist of kind of the decomposition, that's good enough for me. As long as you have a concrete, rigorous argument, then that's good to get you the full marks for the proof. Okay. All right. So any questions about this? But you can't go by. Oh, we're talking about MCQs. In the exam, do we need to prove that the regular language you pick? It's a good question. So here, here you can. This is already regular because you've used a regular expression for it. So what I would recommend is to skip the step where you prove that L is regular, because actually, yes, you would probably need to do that for it to be rigorous. Is just always do L of a regular expression, because automatically L of a regular expression is regular. So you don't need to prove that the language is regular. Okay, so that's a good question and something to note. All right, any other questions about this? Because otherwise, that's it for the material. I was gonna talk about the assignment quickly, but if there are questions about the pumping lemma, I'd be happy to answer them. No? Okay. So the discouraging. So don't be too discouraged by this sort of concept, because really it's just a matter of doing a few practice questions, getting the hand of sort of picking the W, doing the kind of scanning of the XY through your whole string, and then pumping up or down, right? Yes. So assignment. So let me just go look at the So assignment here, just to make sure that I covered everything for you to do the assignment. For talking about context-free languages that are deterministic, in tutorial, so in the extra tutorial that I posted, that's gonna be able to help you out for that. The same thing for this question. Then to show, so designing PDAs, we did this in tutorial 10, right? So using the idea of the stack. And then, so this is either showing that it's context-free or showing that it's not context-free. So with the pumping lemmas, so the material for today should help for that. And so, yeah, so that's the issue here. So these questions are with Turing machines, which you'll see in tonight's lecture. And so because tutorial happens on Wednesday, what I'm going to do is I'm going to post an early recording, which is just going to be, nothing fancy. It's just going to be my recordings that I used for the last session, which, I haven't had any complaints about it. So so if those are okay for you, right? And if you don't want me to, I could, so the PDF, maybe not actually, because the PDF has to be approved by the professor. So maybe I'll see what I can do. Actually, maybe I can put it, I'll post an extra tutorial PDF, and that might be okay. So let me just write that. Right. Okay. And then, oh yeah. So I want to ask for the so because we did a midterm review, right? And then you did the midterm. So was the midterm review at all helpful, like the format, or should it be different for if I do the final review? Was it okay? Okay, it was helpful. Okay, good. Okay. And then what else? Okay, so that's good. And the recordings, right? So if there aren't any complaints about the recordings, right, then I'll also post those for the Turing machines. And yeah, I think that covers about it. So like I said, your assignment 3 grades, you might get them a bit late, but once the other TA sort of gets everything sorted out, then we should be able to get those out to you. Okay. Alrighty. Well then. So thanks for attending the tutorial as always.
So sorry. When is?
Yes.
Sorry. Well, when was the final review?
Yeah. So again, I'm not. I still need to think about it, but so it's the 29th, the final. So it's probably the weekend. So maybe Sunday or probably Sunday, I think. So I'm leaning towards Sunday, but maybe Monday. So that's where my head is at for when to do it.
Thank you.
Okay, yeah, no problem. And it's just that the TA had some personal things to deal with. So once she does that, then she'll be able to mark it. Okay. So again, thanks for coming, everyone, and have a nice lecture, and we'll see each other Wednesday. All right, take care, everyone.